using fatigue, which is my specialty in research. But I will connect this with the additive manufacturing components because these two aspects are very important. And actually, to be able to design against fatigue is very important if you consider additive materials. And this will allow us to use additive material in a wide range of applications. First of all, I want to briefly introduce myself. So I'm actually a professor at NTNU, which is the biggest technical university in Norway. And my current research topics are fatigue and fracture of traditional materials, also fatigue and fracture of advanced material like additive material. I have worked a lot, more than 20 years, on local approaches for fatigue design. And of course, multi-axial fatigue, notch effect, and energy-based method are the strength of my research. So according to my, I had not an easy path in my life. So I start in Padua and I graduate there at the master level. After that, I move to Florence for the PhD. I became assistant professor in Padua, and after that associate professor in Padua, and after that I moved to Norway in 2016, where now I'm the chair of structural integrity. I'm managing a lab which is built dealing with multi-axial fatigue problems. So the main topic of my research you have understood, and of course we have a big group of people, and the lab that I built since 2016 in Norway has the possibility to perform tests at different scales, and also under uniaxial and multi-axial loading is quite well equipped. And actually we are quite proud of the new lab that of course is available for the use of this CRAM project. So dealing with my talk today, I want to divide the lecture in two parts. I want to briefly introduce problems related to fatigue. So I want to give you a basic knowledge about some fatigue issues. And after that, I will go more in detail. We have 2 hours, so I will go more in details on inside the local approaches, which is a very useful tool if you want to design against fatigue. And nowadays we have different possibilities for using these approaches. Starting with the brief introduction, I will say that fatigue is very important because actually 90% of the structural integrity failures are due to fatigue. And this means that actually if we don't consider fatigue, we are losing the opportunity to really design a component properly. And so this is the first consideration that I want to make today. And of course, failure is central to engineering. Every single calculation that an engineering makes is a failure calculation. So successful engineering is all about understanding how things break or fail. And this is the case of fatigue. So fatigue is not a recent topic. The first case that was observed, of course, the first relevant case was the Versailles rail accident in 1842. And of course, from this accident, an German engineer, August Wehler, that was railway engineer that was born in 1819, was able to understand that components can fail at the load that is much lower than the static load if you apply a cyclic load to your component. And so it was the first to propose a diagram that is related the stress amplitude to the number of cycles to failure that is nowadays known as Wheeler curve. Of course, this is a fundamental basic concept that we need to know. And in the Wheeler curve, we have different regimes. We have regimes on the left side, which is the low cycle fatigue regime. We have which is almost corresponding to the static failure of the component at very low number of cycles. After that, we have the decreasing part in the middle, the central part. And after that, you have the fatigue limit or the high cycle fatigue part on the right part of the diagram. And we need also, today we need to speak about fatigue, so we need to have a common language. And I want to introduce some important consideration about the symbols that we use. the symbol that we use mainly is that we apply a cyclic loading to a component, and what it is important for fatigue is the amplitude of the cycle that we are applying is important, the mean stress value of the cycle that we are applying, and these are the two most important points that we have to consider. R, which is defined as the sigma mean divided sigma max, is called nominal load ratio, and is important because is considering the effect of the mean stress on our cyclic loading. So we have different correlations between these parameters in the cyclic. So it's important that you know this equation at least to understand of what we are speaking. I don't want to go in detail here, probably is something that you know very well, but still is nice to present this. And what it is important in fatigue is that the mean stress effect is really fundamental. So if you have a sigma mean that is, so a mean stress that is larger than 0, this is decreasing your fatigue life with respect to the sigma mean equal to 0. And there are different models to take into account this, as you can see in this slide, where, for example, Goodman, Gerber, and other approximate equations are given to provide to be able to take into account of this mean effect stress. So this is an example of how the stress can be strongly be the fatigue behavior can be strongly be affected by the mean stress. So if you consider the case here, you can see that of course the mean stress has a strong influence on the fatigue behavior of your component, and this I will show later will become very important when you speak about defects and when you have a defect inside your component. When you have an additive manufacturing component, usually we have intrinsic pores or intrinsic defects due to the process that are sometimes close to the free surface of the components. And these defects can be affected by a mean stress that can be different from 0 and greater from 0. And so we need to be able to take into account of this effect in the fatigue design. So I want also to say that fatigue failures are not so far in time. So we have different failures that were quite relevant and quite recent around the world. I want to mention, for example, the bridge that fall down in Genoa, in Italy. Of course, that one was not a complete fatigue problems because also corrosion was a main issue there. But of course, the fact that the bridge was designed for the cyclic load of 60 years ago, and now the traffic on the load is completely changed, and also the spectrum of the load is completely changed. So the fatigue perspective or the fatigue load that is applied to the component is completely changed during the time, has created a big issue for this bridge that failed, making actually 42 people died. So in the first part of the lecture, I will briefly discuss what is a crack, how does the crack evolve under cyclic loading, what are the determining material properties, so how does the crack evolve during the time, and how we can predict the remaining life of a component if we have a crack. Very basic concepts that you should know, but I think is important in any case to re-mention this here. So dealing with this part of the lecture, I always refer to these two books. I want to mention that the book from Dowling, it is almost the most widely used book dealing with mechanical behavior of materials. And I want also to stress the fact that in 2021, we have the new 5th version of the book that is available. Probably you don't know yet this, so I want to stress this in this presentation. So what is a crack? So usually it's difficult to define a crack and the crack tip, but the crack is actually a defect that is present in your material from which a kind of propagation start to grow, and we will discuss later what is the crack initiation and what is the crack propagation. For example, in this slide we have a non-metallic inclusion from which a crack is start to propagate due to a cyclic loading. We have also to mention that usually we consider for all our consideration mode 1, but actually in practice we have 3 different modes of failure: mode 1, mode 2, and mode 3. Mode 1 is mainly the failure due to tensile loading. Mode 2 is in plane shear. It's difficult to find a component that is completely subject to poor mode 2. Usually poor mode 2 is not existing in practical application. It's always combined a bit with mode 1. So the most common case is that you have mode 1 plus mode 2. And after that, you can have instead poor mode 3, which is torsion. This case is also difficult to find in practical application alone, but sometimes you can, better than mode 2. But in any case, this mode 3 is also called out of plane shear because it's creating a displacement which is not on the plane of our screen. So it's outside the plane of our screen. And what it is also important that is that all the theory that we have developed for these these modes of failure is considering linear elastic mechanics. So as you have discussed yesterday with Professor Sedmak, the main hypothesis here is that the stress field close to the crack tip has to be linear elastic. This means that the plasticity has a small effect or is not affecting at all the stress distribution close to the crack tip. And in fact, the equation of Irving are based on this consideration and assumption. And so you have the equation that are reported in the slide that are giving to you the sigma in the Cartesian coordinates. These sigma in Cartesian coordinates are valid only under linear elastic hypothesis. And a question is, have we got plasticity close to the crack tip? The answer is usually yes, we have a small volume of plastic material close to the crack tip, but this plastic volume is actually much smaller than the process zone where the K1 factor, the stress intensity factor, is leading the phenomenon. And so we can still use the approximation of linear elastic fracture mechanics. Of course, this is what I mentioned before, the definition of a plastic radius that you can find in your in this slide. And the definition of the plastic radius is changing if you have a plane stress condition or a plane strain condition. Plane stress condition means that the thickness of your component is very small with respect to the other dimension of the component. So it means that actually the stress along the thickness is equal to 0, or you can approximate it with 0. The other extreme case is the plane strain consideration, the plane strain assumption, where you have a thickness that is very large with respect to the other dimension. In that case, the epsilon, so the strain along the thickness direction is equal to 0, and so the is equal to 0 because you don't have deformation along the thickness, and so the sigma z is connected by a simple equation to sigma x and sigma y multiplied by the Poisson's ratio. And in these two different conditions, large thickness or small thickness, you have different value of the plastic radius. That, of course, is smaller in the case of plastic strain because you have a very large thickness and the stress are redistributed differently along the thickness of your components. But you have also to remember that these two cases, plane stress and plane strain, are only two extreme ideally condition. Usually we are in a condition where the thickness also plays an important effect in the fatigue and fracture problems. And I also work on this for a long time. So when we speak about plasticity limitation, we have to remember that if we want to be sure to apply correctly the equation of fracture mechanics, and especially when we have a crack, we need to consider which is the dimension of the critical of the plastic radius that we have in our component, and how the plastic radius evolve along the thickness if you have an intermediate case between plane stress and plane strain. Of course, this concept is valid also under fatigue loading. You have always a plastic deformation close to the crack tip, also under cyclic loading, and the scheme of this plastic radius is reported in the slide. Also, the calculation of how to make the calculation for evaluating the plastic radius is reported here, according to the work made by Doling and reported in his book. So also here it is important to mention that also under fatigue, in the fatigue case, we have a plastic area close to the crack tip, and we have always to verify how much is the size of this area before to make other assumption of linear elastic hypothesis. Usually, I want to anticipate something of what I will say later. High cycle fatigue is always almost in elastic regime, and the small area or the small plastic radius that we have is much smaller than the process volume of the material due to fatigue. And so this means that actually we can consider, at least at high cycle fatigue, a linear elastic behavior for our material. And this will be shown when I will explain better what is a local approach and how the local approach is applied for the fatigue design. So about plasticity limitation, we need also to understand that what it is very important is the thickness effect, which can be considered partially a scale effect, but also a scale effect more general than the thickness effect is always relevant for plasticity limitations, and we need to consider this, as I will discuss with you later. So here another slide that is showing you what I have mentioned before. Usually when you have a cyclic loading or also a static loading and you have a crack, there is a plastic area, but the K field dominate area is larger than the plastic zone. So outside this small plastic zone, you can still approximate your stress field with the linear elastic assumption. And this is very important for all the methods. Usually as engineers, we want to have approaches or local approaches that actually are able to overcome the problem of plasticity. We don't want to use nonlinear equations to solve an engineering problems, because this is increasing the complexity, the computational effort that you have to do. And so this is very, very painful and is very, very difficult to do. So what we would like to do is to have approaches that are easy to use in engineering applications, and to maintain this use of simplicity, we need to be inside the linear elastic field. Another advantage to be inside the linear elastic field is that we can use the overposition principles, which is another important aspect that under plastic deformation is impossible to do. So, I mean, we need to be careful of these aspects. And here is the calculation of the cyclic loading. I don't want to give to go much in the detail. You will have the presentation available later, so I don't think it's important to go inside the details. But what it is important is also to understand that also under cyclic loading you have a plastic volume that is small, but is present in the front of the crack tip. And it is always better to check which is its size before to make any other assumption. This is also very important if you have, for example, a torsional case, because under torsion, usually the energy is mainly deviatoric energy at the crack tip. This means that the plastic deformation is much larger, and so you can find a bit larger plastic volume also at very high cycle fatigue or at high cycle fatigue. So torsion sometimes can be a problem because the plastic volume of the material close to the crack is very large also at low load level, so at high cycle fatigue. Here is how to calculate a crack length as a function of the applied cycles. Usually we make a test on a samples and we measure the crack that is propagating along the length of the crack that is propagating as a function of the applied cyclic cyclics on your component. And you can plot this diagram where you can also derive the slope of these curves that is called dA over dN. Why I'm mentioning this? I'm mentioning this because the most important curve that we know that is able to describe the crack propagation of a crack is due to Paris and is called Paris curve, and it is the curve that is reporting here in this slide. Also in this curve we have three different regions. The first region is the part where we have on the left side the initiation phase, so almost a crack that is initiating, and we have a threshold value below which also if we have a crack nothing is propagating. After that we have the case where the crack is start to propagating in the middle part of the diagram, and where we can actually use the so-called Paris law, which is reported in the slide in the center of the diagram. And after that we have the static failure on the right side of our diagram. But the crack propagation is and the crack initiation especially is a very complex phenomenon. It's not so easy to be described, and still I mean is an interesting topic for research. Is not something that is finished nowadays. It's something that is really a hot topic, and this is due to the fact that we have different phase of the crack initiation, propagation, and growth until failure. The first part is very important, the crack initiation. Usually when we think about fatigue at high cycle fatigue or at very high cycle, the life of the component spent in initiation is almost 70, 80, 90% of the total life. This means that the initiation that is placed at a very low scale, usually in a scale that is comparable with the scale of the grain of your material, is largely part of the life of the entire component. After that, you have the phase of propagation, and after that, you have the phase of growth until failure or rupture. But what I want to mean is that in the initiation phase, different phenomena occur that are very, very important and that are difficult to be modeled, that are due not only to the fact that we have a crack, but is also due to the fact of the material that we are considering on the crack propagation, how the material is affecting, for example, intrinsic and extrinsic mechanism for provoking this crack initiation, and how the crack is interacting with the size of your grains. So this is very, very complex. So for example, if we have a very clear idea of the threshold stress intensity factor for mode 1 case due to some works of Pipan and other co-workers of him, still we have open problems, for example, when we consider the case of mode 3 torsion, and where we are studying the initiation under torsion loading. Of course, there are some interesting contribution by Professor Keisuke Tanaka from Japan, and previously from Keith Miller and John Yates from Sheffield University, but the problem is still not completely unsolved. And where we can use the crack growth under cyclic loading. So the Paris curve is valid usually in the stage 2 of our curve, of our regime, where actually we have the phase of propagation. This is important, of course, for understanding which is the final life of our component if we have an initial crack that we can detect in our component. But you should remember that is still not the main part of our fatigue life in a component, because actually 80 or 90% of the fatigue life is spent when the crack is only initiating. And this is the part where local approaches can make the difference, and where we have to be careful when we are designing against fatigue additively manufacturing components. So this is a scheme that I always like to present to my students, also in the course that I'm teaching here in NTNU about fractal mechanics, which is a very nice and synthetic plot taken by Doling, where you see the how you can derive actually a Paris curve for a material, and how actually you can apply to a real component. Only to summarize a bit what we are discussing here. But as I said, the crack growth under cyclic loading can be seen at different scale levels, and you will always find a place at a small level, at the nano or micro level, where you will find plasticity or extrusion of slip bands that are provoking the initiation of your fatigue failure. So we need to distinguish two words: the material science perspective and the point of view of engineering. The material science perspective want to understand what is happening in terms of material and load interaction at low scale. The designers or the engineers perspective wants to solve the problem of how we can design a components, knowing that the fatigue crack propagation is very difficult to understand, but we need a tool for designing something that is easy, that can be applied with some, of course, mistakes and some, of course, approximation. But we want to have a tool that is able to allow engineers that are facing fatigue problems to design really a component, making some calculations. I belong to this second group of people. So I'm not a material expert, or I'm not a material scientist in this perspective. I'm more on the side of people that want to have tools available for design against fatigue. Of course, these two fields are not separate each other; they are connected. And I mean, we need to be careful that sometimes also when we use local approaches, we have to take into consideration some material aspects that are important. So it's not that we have two separate rooms that are not speaking to each other. We have two rooms that actually have a lot of in common, only a different perspective to look to these problems. And so what it is important for an engineer when a crack is present is to evaluate the residual life that you have in your component. And here is a simple calculation that you probably know very well. But what I want to underline here is that it's possible to make this simple calculation analytically in a closed form. And if you consider which is the most important parameter that you have to detect for using this equation is the initial crack. So actually, you can have a very good approximation of the number of cycles to failure if you detect very well the initial crack that you have in your component. It's not very important, or is not so important to have a clear estimation of the final crack length, because this is not affecting so much the number of cycles that you find at the end. So I mean, you can have a very good approximation if you detect the initial crack. And another important aspect, as I mentioned before, where I wanted to stress this again, because if you have defect, this is very important. If you consider additively manufacturing component, this is a key aspect. What we have to consider is the effect of the load ratio, and uh, and uh, and see that also in the Paris curve, this effect is very, very strong. So if you have a load ratio that is greater than 0, the Paris curve that you have, for example, at R minus 1 is shifting on the left side of your diagram, and the fatigue life is compromised a lot by the presence of a positive mean stress. And again, we have some engineering equation that of course have some approximation and have some, I mean, assumption. But this equation that is due to Walker, that is now alive, and 92 is still exchanging emails with me about consideration of a strain energy density approach for crack propagation, still alive and active. This means that fatigue keep alive also researcher working on fatigue, we hope so. What I want to say is that we have some equations that are able to describe very well the effect of the mean stress. And in fact, if you look to this figure by using Walker equation, we are always to obtain a kind of master curve on the right side of the diagram, where all the points collapse also if they belong to different load ratios. So this is a quite nice representation that we have. In summary, in this first part of the lecture, I have summarized some fundamental concepts that you have seen. I have introduced a bit fatigue and a bit of history. I have discussed with you the effect of the mean stress. I have introduced the different modes of failure. I have introduced to you the plastic effect that we have always present if we have a crack, but we have to consider it locally because usually this is very local and concentrate only in the initial part of in the vicinity of the crack, but outside this region we can use linear elastic fracture mechanics, and we have powerful tool like Paris curve and for example Walker equation to be able to estimate how the crack growth and how is the remaining life of our component if we have initial crack that we can detect and we can measure inside our component. Now I want to introduce local approaches for fatigue design, which is the core part of this lecture. Probably the original part that I can give to you, because the previous part is something that you can find in many courses that you have attended. But about local approaches, I have worked with Professor Lazzari and the group of Padua for more than, I think, for more than 20 years now. I started my master thesis there, working on some local approaches, and I have continuously worked on that, and now I'm applying these approaches to fatigue of additive manufacturing components. So I want to explain you why fatigue is local and why local approaches can be a useful tool for design. I want actually to convince you of this. So this part of the lecture will have a short introduction. We'll discuss notch and geometrical discontinuities. We'll discuss in detail local approaches, the main approaches that are available, not only the one that I have developed. Defects and fatigue design that is very relevant for additive manufactured components. And here I will cite Murakami approach and also other approaches that are linked to the Kitagawa diagram. I would like to also discuss with you multi-axial loadings, and I will especially stress the importance of a method that is developed by Fatemi Sossi. And I want to show you some application to additive materials, which is the final part of this presentation. Dealing with the introduction, I want to say that what it is very important is that a component additively manufactured has the complexity that is increased a lot with respect to traditional components. So one of the main problems that we have is that if you also apply tensile loading of the component locally, you have always a triaxial state of stress that is present on your geometrical feature of the component. On the other side, you have the defects that are due to the process that are interacting with this complex geometry. And this makes the difficulty to really design against fatigue this component printed by additive process. So the main challenges that we have with the design against fatigue additive manufacturing components is the design in presence of geometrical discontinuity, safety in presence of defects due to the process, and assessment in presence of complex loadings, I mean complex triaxial or multi-axial loading. We have different approaches for fatigue design that we can consider. But of course, for additive manufacturing, safe life design where you have infinite life is not an approach that you can apply, because mainly you have always defects that are present on your component. So you have to survive with the defects and understand how the defects interact with the fatigue behavior of your component. I will skip this slide, is only to understand a sketch for understanding how we can design against fatigue. But I want to put the stress why fatigue is local. Usually we design very large components. For example, this is an example of an engine of an aircraft. Or we can make other examples that are built for civil construction engineering. So big, for example, components that we use and that are subject to cyclic loading. Usually we have to design these kind of components, and the fatigue problem or fatigue initiation life or fatigue propagation life always start from a localized place inside our component, and where the crack, for example, is very small in scale with respect to the size of the entire component, that can be, for example, meter, while the crack can be 0.1, 0.01 millimeter. So we have a span of scales from the crack length and the real component. A small defect can be really very dangerous for a large component, and this is the key of why fatigue is local. So usually we have a multi-scale nature of fracture, but also of fatigue problems, where we can see the approach, where we can see the different scale levels that we are considering, going from the macroscopic failure, so meter in terms of size, until the atomic scale. So this means that it's really a very large or wide range of scales that we are considering. And usually the initiation phase is at the micro nano level. So a defect that is at the micro nano level can create the failure that you can see here in the slide, that is a failure that is destroying an entire ship. So as I have discussed before, we have crack initiation, crack growth, and final rupture for your component. And here is an example of a crack that is starting from the component. We have after that the progress of the crack and the end of the crack. And at the beginning, the benchmarks that are typically of the crack propagation due to the cyclic loading. So what I say usually to my student is that if you have a cold, you can go to your family doctor, but if you have a fatigue problem, you need really a specialist. So fatigue is a very local phenomena, and a structure of several meters in length can fail for a crack or a defect that is less than 1 millimeter. So we need to be very careful how to manage fatigue problem, and this is also the why there is still interest in these fatigue problems, because it's still a challenging topic to be faced. Another important aspect that we have to consider is that nowadays we know that we have low cycle fatigue, we have high cycle fatigue, but we have also a kind of very high cycle fatigue or ultra cycle fatigue. That is a regime that we can reach now with the resonance machine or other machines, where the failure is not due to defects that are on the surface, but the failure is due to the defects that are starting from internal inclusions. So usually, if you consider the morphology of fatigue initiation, we have three different morphology. The morphology for low cycle fatigue on the left, the morphology of high cycle fatigue, where you have usually an initiation from the surface, and after that, very high cycle fatigue, where an internal defect can create a problem. And this is the reason, because to evaluate the very high cycle fatigue of additive manufacturing components that are sometimes affected by defects is a very important and nice topic to develop, and is a topic of hot research nowadays. This is an example of the so-called fish eye that is reported in a paper by Professor Yoshi Hong, editor-in-chief of Fatigue and Fracture, which is the journal where I'm also working. And it shows to you that the crack is initiating from a subsurface defect, which has a typical shape of a fish eye. Another important aspect that we have to consider for additive manufacturing components is the surface finish effects on fatigue limit. You know that in additive manufacturing component can be print as built or can be used as built, so directly taken from the process, or we can machine them after we have print them. It's important to understand that this can affect tremendously your fatigue life, and you have to consider this in your fatigue design. Of course, as engineer, we will prefer to use the component directly 3D printed from the process, but sometimes this is not possible. And another important aspect is that this effect of surface finishing is much more important for high strength materials. So if you have a very, very high strength material, this material is much more sensitive to the surface finishing. This means that if you have a noble, a kind of a very, very respectful material in some way, you have to treat him very well. So the surface finish has to be improved. If you have common steel that is used for common construction, is not so sensitive to the surface finishing. So we have to consider this aspect also in the cost for the design, because sometimes we are facing the problem of costs for additive manufacturing, and sometimes it's not a good choice to increase the strength of the material if you are also not treating the surface properly. Sometimes it's better to use a low material, a low performant material, but and treat this material with for example, not a very detailed surface finishing. This reduces the cost and you have the same effect. This is the effect of an example of the defect of the surface finished. If you have a forged surface or if you have a polished surface, the fatigue life and the fatigue curve is changing completely. And of course, this is very important if you consider the additive manufacturing components, because this plays a fundamental role in the fatigue life. You always have this kind of roughness surface in additive material components, and you have to decide if this can be acceptable for your fatigue design according to the service load of your component, or if you have to improve the surface finishing, treating the materials and the surface in a different way. The decrease of fatigue is very, very large, as you can see in the red fatigue curves reporting in the bottom of this slide. Dealing with additive materials, so we have different challenges that we have to consider dealing with dealing with fatigue. I mean, it's important to consider the building direction, the surface finishing, and also residual stresses, the post-treatments, and the coatings that we can do. All these aspects have a very high level of importance, and this is the reason because fatigue behavior of additive manufacturing materials is still an open field of research where we can almost work for many years now. As I shown before, notch and geometrical discontinuities are always present in additive manufacturing components. So we need to understand how to treat these notch and geometrical discontinuities in some way. And I want to mention that historically the problem is not new. It was studied before by top researcher. I want to mention here a German engineer and professor Kirsch, Stefan Timoshenko, and James Coudier, that were the first to be able to study notch effect in a very simple problem, the problem of a circular hole. So a plate weakened by a circular hole. This case probably you have seen many times also in your books. But this is important because this is the first solution that is available where we have a closed form solution for studying the problem of a notch. And of course, you have to think this circular notch also, for example, like a defect in your component. It is not only a notch, it can be also considered like a defect inside the material, and you can use the same frame of equation for studying this kind of defect. So the question that Timoshenko and the other researchers want to answer is which is the stress amplification or stress concentration factor that you have due to the notch close to the notch tip. Timoshenko put some boundary condition that I don't want to describe here in details, but is mainly due to the fact that you have the free edge on the notch, so you can put some stress equal to 0 on the edge of the notch, and you can impose this equation easily. And after that, you can impose the so-called iris stress function, from which you can derive the stress field distribution of the notch. I don't want to go in details of this, but I want to say that you have some tools that are giving the stress distribution also in presence of notch discontinuity. And you have this distribution of stresses close to the notch tip. This means that you have a strong amplification of the stress field close to the notch edge due to a nominal stress that is much below the value of the stress peak of the stress that you find on the notch, on the edge of the notch. And this is the typical example. The amplification for considering a large plate with respect to the diameter of the circular hole give a stress concentration factor of 3, which is well known. And of course, it's the first case where we have a closed form solution for a notch component. Another worth mentioning contribution is the one from Inglis, that in 1913 was able to study the problem of an elliptical hole. This is very, very interesting because if you consider an elliptical hole, is not so far from the shape of a crack. Actually, if you consider that, for example, the larger diameter or the larger semi-axis of the ellipse is elongating a lot with respect to the minor axis, you are almost converging to the crack case. And this is the reason because actually this work from 1913 is considered one of the work that started the way of fractal mechanics considering crack problems, because actually you can extend this approach to linear elastic fractal mechanics in some way. And English was able to provide also the stress concentration factor for the elliptical hole. What it is very interesting is that if you look to the equation on the upper part of the slides, we have a stress concentration that is 1 plus 2, and the two semi-axes divided one each other. So this means that if you increase one semi-axis with respect to the other, putting, for example, B tending to 0, you have a stress concentration factor that is tending to infinite. So this means that a point method, like the stress concentration factor, at a certain point is not valid for any consideration in front of the notch. And you need to introduce a field parameter, not a point parameter, to discuss what is happening in ahead of your notch component. After that, I want to say that according to my experience, the most useful contribution dealing with notch component is due to Lazzarin and Tovo. This is a generalized notch solution provided in 1996 by Professor Lazzarin and now Professor Tovo. Tovo was previously a PhD of Professor Lazzarin, and after that they worked together for several years developing this equation for notches. Actually, they consider a notch with a specific notch opening angle that they call 2 times alpha, a notch tip radius that can be also 0 if you want, and the notch depth A, which are the main geometrical parameters. And they were able to use the complex potential formulation, in which I don't want to give you the details, but it's only to show that the problem is really a complex problem, both in terms of complexity and also because you use complex potential to solve it. They were able, imposing very difficult boundary condition, and according to a very difficult curvilinear coordinate system that they were introducing for solving this issue, they were able to provide some nice equation that are mode 1 and mode 2 equation that are able to give you the stress distribution in front of a notch, independently of the notch tip radius, independently of the notch opening angle, and independently of the notch depth. This means that these equations are able to consider together all the main geometrical parameters, and they are not difficult to be applied because actually we have all the parameters that we need as a function of the notch opening angles that are reported in tables. So it's very simple to apply this equation to in practice. What it is also important to mention, as I mentioned before, is that the stress concentration factor is not a parameter that you can always use. When you have a notch radius that is small, or tending to 0, you have to actually leave the point method and the method where you are only considering the peak stress at the notch tip, and you have to go in the direction of the notch stress intensity factor, which is an extension of the stress intensity factor that we use in fracture mechanics. This is a field approach, so we are measuring the stress field ahead of the defect or the crack or the notch, not the stress on the tip of this defect. And we are evaluating a field parameter that is able to describe the stress intensity in front of this region. A very typical example where we need to define a stress intensity factor is, for example, the special case of weldments. If you consider, for example, the weld toe or the weld root of a weldment, like the cruciform joint that is reported in the slide, you can model this weld toe like a sharp notch with an opening angle of 135 degrees. And of course, you can apply the equation of Lazzarin et Ovo, putting the notch radius equal to 0 and putting the proper notch opening angle that is 135 degrees. And you have the equation for mode 1 and mode 2. The validity of the equation was proved in different works by Lazzarin, Tovo, and after that I also work a bit with Professor Michele Zappalorto on these topics later. And we proved that the equation were working very well, and also we improve in some regard the equation, keeping into account the finite dimension of the components and different aspects that can be considered. I want also to mention that Lazzarin and Tau equation are not the only equation available for notches. There was a previous equation that was made by Neuber, and that I studied during my master thesis in 2002 with Professor Lazzarin. Actually, we extend this equation and modify the Neuber equation to be able to study the problem of a notch, but the formulation is much more complex than Lazzarin and Tovo solution, and has less possibility to consider all the geometrical parameters. But I want to make clear that Lazzarin and Tovo is not the only solution available. There is also Neuber modified solution that I developed with Professor Lazzarin in 2003. And after that, we published 6 years later with Professor Radai in 2009. We proved the equation and we compared the original equation from Neuber dated 1958 with the equation that we modified, showing that actually our equation was working very well. But what I want to mention is that if you want to design against additive manufacturing, you have to face complexity in your components, and so you have to at least understand what is a notch, what is a geometrical discontinuity, and what is a point-based approach, and what is a stress field-based approach. Because if you have a sharp notch, you have to consider a stress or a notch stress intensity factor parameter. If you have a blunt notch, you have to consider a point method. But in any case, you have to be able to consider a notch properly and to consider how it is the stress distribution ahead of the notch. The complexity that we can achieve with additive manufacturing is good, but at the same time is creating a lot of problems because we have complexity in geometry. So dealing with the local approaches, I want to start with the first approach that I considering interesting for fatigue purpose. And this approach is probably the oldest one. Is also the only local approaches that up to now is reported in a standard for design. And is reported, for example, in FKM standard, which is the standard in Germany. And is also reported in some way in some IIW recommendation and also mentioned in the Eurocode now, in the new version of the Eurocode that will be delivered soon in the next months. The idea is that the method is the Neuber method, is called fictitious notch radius. It means that usually what Neuber wants to do is to consider the real notch, but he knows that it's difficult to have, due to the consideration that we make before, the stress concentration factor is not well representative, because if the notch radius is small on the real notch, the stress concentration factor is not giving you the real picture of the fatigue behavior of your component, for example. And so this means that the real notch is not representative. So what we can do is to average the stress over a certain distance close to the notch tip and consider this average stress as our critical parameter for fatigue design. So this means that we are considering a kind of integration of a stress along a support microstructural length that is called here rho star. And this gives us the possibility to have an estimation of the fatigue life. So this is the first actually attempt to use a kind of critical distance approach, because we are using a stress average over a volume of material over a line mainly. But of course, Neuber also wants to translate or to transfer this tool to engineers, and engineers do not like to make integration every time. So he proposed a simple equation that gives us a fictitious knot radius that is called rho f, that is a larger radius with respect to the real radius that we have in the component, but for which we can measure the stress concentration factor in one point. This stress concentration factor of the fictitious notch radius is automatically taking into account the averaging that we made in the integration part on the left side of our diagram. And so again, with the point method, we are able to give an estimation of the fatigue life. So actually we are now bypassing the problem of the stress field methods, simply considering an enlarged fictitious radius that is giving to us a description of what is happening on a point. And of course, radii apply this to different materials, also being able to estimate this microstructural support length for cast steel, austenitic steel, aluminum, magnesium alloys, and steel, and other different of steels, according also as a function of the yield strength of the material. And what we made with Professor Lazzari, if you look to this equation, what is interesting to see is that we don't have any dependence on the notch opening angle, while we know that the notch opening angle is not so negligible in the final application of this approach. So from 2009 up to 2014 with Professor Lazzari, we work a lot on this field, and actually we consider the initial discussion of radii, that was to consider the fact that for weldments we consider the worst case consideration with the real radius rho equal to 0, a rho star, which is typical for steel, that is 0.4 millimeter, and 2.5 as S, which is a multi-axial parameter considering the stress distribution that is close to your defect. And the final fictitious radius is a constant according to this method and is equal to 1 millimeter, without keeping into consideration at all the notch opening angle. This is what it is up to now reporting the standard. So this is quite conservative, because we know that if you consider this configuration, you are referring almost to a notch that has an opening angle equal to 0. But if you increase the notch opening angle, you actually improve the fatigue life, because the stress field is decreasing. So this equation is very conservative and is really the worst case configuration that we can mention. This is exactly what it is reported in the standard for weldments. You have this local approach for fatigue design, where both at the weld toe and at the weld root, you report the radius 1 millimeter without keeping into account the notch opening angle. What we have made with Lazzari, after a lot of work and a lot of analytical calculation, is to develop a method that was able to take into account also the effect of the notch opening angle on the evaluation of the fictitious radius. And here you can find the step that I used still when I was almost a master student. And the equation, the final idea was to find out the value of S, so the multi-axiality value of S, and showing that this value of S is strongly influenced by the notch opening angle. This means that the fictitious radius is also influenced a lot by the notch opening angle. So this diagram is summarizing a bit what I mean. I mean that it's true that if we have a notch opening angle of 0 degree, 2.5 is correct, and so I found 2.42 here, and so we can apply a fictitious notch radius of 1. But if you have a notch opening angle of 135, S is equal to, for example, 5.22. This means that you have a mistake, or you are too conservative of 200% with respect to the case that is reporting the standard. So this means that the notch opening angle has to be considered as important aspect for applying this method. And here I'm reporting what we obtain again as a function of the notch opening angle, and this is what is reported in the table is again S, which is the parameter that is taking into account of the geometrical aspects of the notch. There was a researcher that was able to apply to different configuration the notch rounding approach to components subject to fatigue, and this cutter with a lot of points was reported, also providing very nice curves for engineering design. What it is evident from this curve is that the scatter is very large. And the problem is that the scatter is very large. Sometimes the points are very above the fatigue curve that we are suggesting. And this is due to the fact that we are not properly considering here the effect of the notch opening angle as it should be done. And this is the main contribution that with Lazzarin I did for this topic in several years. Of course, we also applied the same to thin joints. That is another critical point where you can apply this approach, and where Professor Sonsino contribute a lot on the topic. Another very important approach that I want to mention as local approach for notches or for design against fatigue is the theory of critical distance. The theory of critical distance is a very nice approach that was developed by mainly by Taylor from 1999, where the first paper in International Journal Fatigue with 464 citation is published, and after that, Professor Lucas Susmel and other collaborators work with Taylor to establish different procedures for applying point, line method, and area method to different kind of loading modes. I'm reporting here the two, mainly the two books where you can find these, the summary of what they did on the topic. The idea is based on the initial idea of Neuber of averaging the stress over a material parameter length, which is L, which is the critical distance, that can be estimated in some way according to the material property that you have under fatigue loading. Of course, you have the point method, the line method, and the area method according to what you want to measure. The point method is saying that what it is important is a point at a certain distance from the notch tip. The line method is saying that what it is important is the average or the integrate stress over a certain distance in front of the notch tip. And the area method is saying that what it is important is the stress average over a control volume. I want to mention that before Taylor and before Susmel, as nowadays also Susmel and Taylor are saying, there are previous people that made this development of critical distance. There is a work from Peterson in 1959 that is using the averaging approach like a theory of critical distance for fatigue estimation. Tanaka in 1983 made a equation for fatigue strength due to this method. Taylor, of course, in 1999 was able to formalize very well this approach, but also Severin before in 1994 used this approach dealing with the sharp notches. And here I want to mention the work of Tanaka, especially that is actually the first work where the critical distance was almost formalized in 1983, so 2 decades before Taylor. And a work by 1991 made by Shepard, that is now teaching still in Stanford University, that where she was able to apply for the first time a kind of critical distance in a volume of material in the front of a notch. So I want to say that sometimes you find things that are made by different people in parallel in different places of the world, and after that, the final results, of course, is due to Susmel and Taylor, that provide a very good comprehensive summary of this approach, applying this systematically to different components. But the initial idea was also in other works. And the first that I want to mention is, of course, Professor Neuber, that was the first really in 1958 to provide the idea of stress averaging. And the fictitious notch radius approach is actually the same idea, but with the advantage that you are also going back to a point method, because the fictitious radius is also giving you the possibility to go back to the stress concentration factor for the fatigue analysis. This is the work by Severin, where he applied the same criteria. And this is the point method, line method, and area method as developed by Susmel and Taylor. Of course, the Professor Susmel and Professor Taylor made different interesting application of this also to static loading, and also to multi-axial case. This is a paper that I like a lot from 2008, where they were reporting the study of V-notch components under static loading and subject to brittle failure. And they were able to summarize a lot of data with different combination of loading modes in a single scatter band using the theory of critical distance. This is again the same paper. And this is again the same paper where they also apply the approach to the experimental cases by Severin dated 1994. Another local approach that I have just mentioned before, but I want to recall now, is the notch stress intensity factor approach. And the first to define a stress intensity factor for notches were Gross and Mendelssohn in 1972. The definition was after that reused by Professor Lazzarin and Professor Tovo in their generalized equation, but they maintaining almost the same format of Gross and Mendelssohn 1972. The idea is that what is governing the failure is a stress field parameter that is called K, that is the extension to a notch with a different opening angle with respect to the crack case. So is an extension from the case of the linear elastic fracture mechanics. What it is very interesting for this K or notch stress intensity factor is that it is able automatically to include in all the calculation the scale effect. So this means that actually is not like the stress concentration factor, that if you scale the geometry up or down in proportion, is not changing its value. The stress intensity factor is completely fully sensitive to the scale of your geometry. So if you are scaling up and down a geometrical component of some scale, you can actually, with the stress intensity factor, capture which is the variation of its value, and which is the fatigue reduction that is changing for a large component with respect to a small component, according to the equation that is reported in the slide. The first trial to use this notch stress intensity factor to a very significant case in practice was done by Lazzarin, Tovo, and Livieri in, I would say, 2001, when they started to summarize welded joints from very different, with very different thickness and very different geometries, subject to different loading. combinations. And what they were able to show is that the method of the notch stress intensity factor is able to summarize all the data in a single scatter band independently of the geometry, scale, and dimension, is only dependent on the material. So for example, for steel we have a scatter band, and for aluminum we have another scatter band, but this is almost closed independently, is not dependent on any geometrical parameters that the delta K is able to take into account. So this is a very strong unifying parameter that is able to take into account scale effect, geometrical parameters, and all what you need for a real proper fatigue design. After that, I want to mention as local approach the strain energy density. That is the approach where I work more with Professor Lazzarin. I started during my master thesis in 2001 and 2 when Roberto Zambardi was still a PhD of Professor Lazzarin, and we work on this approach from 2001 to 2014 until Professor Lazzarin died for more than almost 13 years. But of course, also here the literature is not only Lazzarin. Before Lazzarin, there were other strain energy density approaches developed in the literature. It is always nice to mention them because it's the pioneering contribution that we have in the field. And what it is really nice is to show that the first one to consider as the energy as a useful parameter for design was another Italian, Beltrami, Eugenio Beltrami, in 1885, where he studied for the first time the linear elastic strain energy density in components, not in notch components, but actually in standard components. And he considered this a critical parameter for the fracture and not for the fatigue prediction, because fatigue was not very well known at that time. But it's nice to mention this. And after that, of course, Professor C contribute a lot with this method, that is a point method able to evaluate the strain energy density in one point, and other apply the strain energy density in a different way, like Professor Grinkan and Professor Elling, to different kind of components and materials. Here I'm reporting the picture of Eugenio Beltrami. And I want to mention which are the advantages of the strain energy density. The strain energy density is able to consider the scale effect, because is automatically including the notch stress intensity factor, is able to consider the contribution of different mode, permit to consider the cyclic nominal load ratio, permit to consider the effect of different geometrical features, so is automatically including the effect of the notch opening angle, overcome the problem of multiple crack initiation and their interaction, because the volume of material, as I will show later, is in front of the notch tip, and so all the crack are initiating in that volume. The said value can be evaluated with coarse meshes. I will discuss briefly with you this, and this is very important because you can actually use very coarse mesh also in three-dimensional case. And if you are able to make a three-dimensional model, automatically it includes also all these three-dimensional effects. The strain energy density formulation is quite complex in principle, but the idea is easy, is to average the strain energy over a control volume R0, and the control volume R0 is a material property that we can define according to some material property of the material, as I will explain later. The analytical formulation is also sometimes complex, but the strain energy density final calculation is very simple. Is the last equation, where you have actually the average energy that is a function only of the stress intensity factor K1 and K2, the notch stress intensity factor K1 and K2, and of R, which is the actually the radius where you are averaging the strain energy density. So these are the two main parameters. E1 and E2 are simply angular function due to the integration of the energy along the inside the volume. And actually, the final equation is very simple to use. Is this one? is reporting delta W as a function of delta K1 and delta K2, and as a function of the critical radius R0. And R0 is the control volume, which is a material properties. E1 and E2 are shape function which depend on the notch opening angle and Poisson's ratio, but we have a simple equation that allow to calculate these functions. And after that, I mean, the equation can be easily applied to any component. I omit here the mode 3. Is also possible to extend to mode 3, but this is a more complex case. I will touch a bit this later. We extend with Lazzari in 2005 in a paper the idea of the notch of the strain energy density applied to blunt notches. So we generalize actually the approach to any shape of notch components. And we were able to provide another very simple equation that is giving to us the strain energy density as a function of a generalized notch stress intensity factor that is also able to take into account the notch radius and not only the opening angle. So this is a more generalized expression of the strain energy density that we developed with Lazzari in 2005, again during my master thesis. What is the critical radius R0? The critical radius R0 is a material property that can be obtained very easily from two standard tests. The first test is the test on a notch component, and the second test is the test on a crack component. On the crack component, you can measure the fracture toughness under static loading, and on the notch component, you can measure the ultimate strength. And the critical radius is easily found in this slide. Is also a function of the Poisson's ratio and can be calculated as these two extreme case: crack component and notch or uncrack component. This is why this, because what we want is that the energy is the governing parameter for our component. This means that actually the energy for a crack component has to be equal of the energy for a notch component. So if you make an equation between these two energy, you find out that the critical radius is a function of the fracture toughness and ultimate strength of the material under static loading. Dealing with static case with Lazzari, I made a lot of work to summarize more than 900 data. I would say that nowadays we have probably summarized 2000 data dealing with static failures. And we report the first time this scatterband in a conference where we were invited by Professor C and Professor Alexander Korsuski, editor of Material in Design in Oxford, where I was invited to my first plenary lecture, where I present for the first time this scatterband. That after that we improve a lot with different data that we produce or we take from the literature. What it is interesting to note is that this scatterband consider materials that have an ultimate strength ranging from 2.5 megapascal to 1200 megapascal, and the fracture toughness that is ranging from 0.15 to 55 megapascal square of meter. And also the notch opening angle was varying from 0 to 150. So a lot of variation in geometry and a lot of variation in materials. And after that, we apply the same concept to welded joints, reusing the data that Lazzari and Livieri published and according to the stress intensity factor approach in 2001. So how we make this? We apply the critical radius evaluation considering the welded joints without any stress concentration, quindi so a kind of a notch component. And after that, we consider the case of a weld toe, and we equate the two, or we make the equation of the two energy density, the one from the unnotched case and the one from the notched case, and we evaluate the critical radius R0. Actually, the main parameters are reported here, and the typical value for steel that are reported here give a value of the critical radius that is almost 0.3 for welded joints made of steel. And this is the curve that we plot together with Lazzari, reported in several papers later, because this is the standard curve and our master curve for design that we reuse many times in our academic life as a benchmark for different applications. And what it is interesting to note is that this scatter band is nowadays including in the first version it was including 900 data, but nowadays is also including more than 3000 data taken from the literature and following the new trends and developments. So it's quite update curve. I mentioned before that the strain energy density has the advantage that you can use a coarse mesh. This means that usually when you have to measure a stress intensity factor, you have to use a very refined mesh because you have to evaluate the stress, and after that from the stress you have to go for the evaluation of the stress intensity factor or for the notch stress intensity factor. For the strain energy density, this is very different because commonly used finite element software actually use the displacement for the calculation of the strain energy without passing through the stress or the strain. This means actually that you don't need to refine too much the mesh, and you can use a very coarse mesh for the final evaluation of the energy inside the control volume. For example, this is a kind of work that we made in 2009 with the Professor Lazzarin to show the effect of the coarse mesh on the final accuracy in calculating the energy and the the notch stress intensity factor. You can see in the slides that with the fine mesh and with the coarse mesh, actually we obtain almost the same results. So this means that actually we don't need for the strain energy density application any fine mesh, and this is very useful for practical application. We apply this to three-dimensional models. That is the most interesting case because in this case you have really a lot of difficulties in modeling the component if you have to use a fine mesh. And what it is very nice here is that actually you can really mesh the component with the coarse mesh. Here we use a regular mesh, but and in the control volume we put only few elements. Here we put, for example, 4 elements. But we made a trial with different range of elements, and what we obtain is that also with 4 elements inside the control volume you can apply very well the method. So this means that this is a very powerful tool for practical application. The majority of this work on local approaches is reported in Material Science Engineering R, which is a quite prestigious journal. At that time, in 2014, me and Lazzarin that wrote this paper, we are the first Italian to publish in this journal which has an impact factor of almost 30 now and a 5 years impact factor of 43. So it's quite interesting. And you can find all what I have discussed about local approaches mainly in that review paper. Of course, we collaborate a lot with different researchers around the world. Here is a picture where we are with Jan Patterson, with the Professor Radai, me and Professor Lazzarin, and Professor Lazzarin and Professor Murakami in Trondheim. And I want also to mention that a nice synthesis of these local approaches is made in the book of Dieter Radai and Michael Wormald that is called Advanced Method of Fatigue Assessment that was published in 2013. It makes a good summary. It's not updated in terms of new data, but at least the principles are reported there for the advanced criteria for fatigue design. And of course, we made several papers dealing with this that are published. Another problem that we have with I will touch now very briefly 3 different topics. We have still half an hour, so I will go through 3 different aspects that I would like to summarize here. The first is the problem with defects and how we can design against fatigue in presence of defects. The second is the multi-axial loading, and the third is some example of additive materials. So what it is important to know is that again, the study on defects is not new, And there is a very famous diagram that is called Frost-Miller diagram that is dated 1960. The book from Puck Frost is probably from 1968, so it's a very old book. But this diagram is relevant nowadays for designing against additive manufacturing. This diagram says to us a very important thing. Says to us that first of all, the stress concentration factor KT is not a governing parameter if we have long cracks or if we have sharp notches, because you are actually underestimating too much the fatigue failure of the notch, and so you are too much in the safe direction, because the stress concentration factor is not acting anymore as a parameter that is suitable for the fatigue design. Another aspect that is given to us this diagram is that on the other part, on the blunt notches, you can still use a point method, but you have to be careful to use the point method when this is applicable and when is something that you can really trust. Another important aspect that is mentioned in this diagram is that for certain value of cracks that are below a certain length, you don't have any crack propagation, and you can have some sleeping cracks or sleeping defects that are present in your component without creating any issue at all for the final fatigue life. So we need to distinguish which are the critical defect and which are not the critical defect for our fatigue design. So here is, for example, an example of a non-propagating crack propagating from a drilled hose. This is taken from the book, from the famous book from Murakami, and this is taken from some of my works with Professor Lazzarin, Tov, and also with Professor Yates, where we found some cracks that were not provoking failure inside the component. They were actually cracks that were at a certain point initiating, but never propagating. They stopped and they never propagating again. And so what it is important is to define what is for us a critical defect when we design additive manufacturing components against fatigue. So again, a fundamental concept that is old but new for additive material is the concept of Kitagawa diagram. So A0. A0 is a length, or is called intrinsic material length, and is a kind of a threshold for our material. If we have a crack that is larger than A0, or a defect that is larger than A0, we have a propagation of this defect in the real service life condition. If you have a defect that is smaller than A0, that is our threshold value, actually we have sleeping cracks or non-propagating defects that of course are present in our component but are not so dangerous for our final fatigue life. So this is a very important concept. A0 under fatigue loading is linked to the threshold value of the stress intensity factor that you can achieve or you can obtain from the Paris curve, and the stress intensity and the stress range of the notch components that you can find in the from a notch components. It's very easy to see that this A0 is very similar to the critical distance measure L that Susmel and Taylor are reporting, and other researchers are reporting later. But this work was made in 1979, so 20 years before. And so everything is here connect. And of course, there was not so wide access to the literature that time, and so this is the reason, because different researcher works in parallel to these aspects, taking and tackling different perspectives. Lazzarin and Azzori, that are reported here in the slide, extend this diagram, Kitagawa diagram, also to the notch components, introducing a third part of this diagram on the right side of the diagram, and we are able to really evaluate the effect or the fact that we can consider, for example, stress concentration factor as a valid parameter from point C and D of this diagram in the middle of the diagram, you have to use the linear elastic fracture mechanics, and on the left part of the diagram, you have to use actually the unnotched material properties, because the cracks are not affecting your fatigue life. So this is a very nice diagram. And Lazzarin and Lazzarin, Azzori and Meneghetti in 2003 were able to extend this diagram, also take into account the scale effect with a very smart and nice design of this diagram. They, of course, apply this diagram to different materials, steels of any kind, and they were able to show how the diagram, how the approach is working very well, considering, of course, the presence of defects, presence of notches, and presence of unnotched materials. So the diagram is describing all the area of interest that we have with additive components. It is very nice to mention this. In 2005, with Lazzarin, we also extended the diagram using the energy approach that gives again the advantages to be mesh independent, that give the advantages to be quicker to be applied, and give the advantages also to be scaled very easily to different scale, also at the nanoscale. So usually when we have additive manufacturing components, we have notches and we have defects. And here in the slide, I'm reporting a case where we have a notch component, semicircular notch, V notch with 1 millimeter of notch radius, V notch with 0.1 millimeter, and different size of defects that are reporting according to the area that are plotted in the first figure. The size of the defect is almost proportional to the area that is in red in the figures. And what we did was to apply the strain energy density to see if it was able to summarize the data inside a single scatter band. So we find out that it was possible for V notch and for circular notch and for any kind of different geometry to summarize it. So this means that in this specific case, the effect of the defect is less important than the effect of the notch. But sometimes you don't have this, and so you have to be very careful. I want to mention this case only to show you that sometimes we have the advantages that the stress concentration that we have inside the additive manufacturing component is playing a fundamental role more than the defect itself if you have a complex geometry. And so in this case, we have an easy way for evaluating the fatigue life. If you have unnotched components where the defect mainly has a primary role, that is another story. In that case, I would suggest to use Murakami method. That is very good because it's able to correlate actually the fatigue limit of your material very easily according to a simple equation that is a function of the square root of area of your defect. So actually the idea of Murakami is that to correlate the fatigue limit of your material with some other material properties that are linked to the weaker hardness of your material, but the most important parameter is the square root of the area that can be on the surface or can be an inclusion. Okay, and this will allow you to predict the fatigue life of your component also in absence of the notch, only in presence of a defect. Actually, Murakami in 2019 with a group of other researchers in Japan, Murakami is now retired but still very active in research, was able to apply this method to different materials produced by additive components. And the paper that I mentioned and the figures that I'm mentioning are taken from a work from Murakami dated to 2019 in International Journal of Fatigue. And after that, of course, he applied to different materials. This is an old picture taken from his book dealing with other materials. But what I want to mention is that if you have a defect, we have some tools developed in the past that can be useful for predict the fatigue life of your component. And actually, additive materials and Murakami method are very interesting because they can be connected together, and the Murakami method can be easily applied to additive material in presence of defects. So this is an interesting point that I want to mention you today. I'm also mentioning another paper by Murakami on Inconel that is again published in Fatigue in 2019. Dealing with multi-axial loading, I want to mention only briefly what I think about this and which is the main point of this in this lecture. I want to mention multi-axial stress problem because as we have seen in the previous slides, with additive process, you can print really complex geometries. This means that if you also are applying a uniaxial load to your components, locally you have always a multi-axial stress state. And this means that you have, as engineer, to be able to understand how to manage this complexity or this complex multi-axial stress field close to the notch discontinuity or close to the defects. And I want here to introduce only the most significant, I would say, approach that is due to Fatemi-Sossi. Is not the only one applied for multi-axial stresses, but is of course the most cited. You can find many reference on it, so is trustable, and you can find a lot of work done using this method. The idea of this method is that is a critical plane approach that almost attempt to reflect the physical nature of fatigue damage, and is called Fatemi-Sossi model. Now we will discuss a bit the parameters inside the model. The parameters are very simple, and the parameter governing the fatigue damage are the maximum shear strain amplitude and the maximum normal stress acting on the maximum shear strain amplitude plane. So the idea of the method is that what they want to do, Fatemi and Sossi, was to model or have a criteria that was able to capture the physics of the initial shear phenomenon that is happening anytime you have a crack initiation phase. And so the equation that is reported by Fatemi-Sossi is expressing actually a constant C that can be obtained as a function of the delta gamma max multiplied by a function which is a function of the normal stress max applied in the critical plane. So you have to identify the critical plane, and after that you have to find the normal maximum stress in that plane normalized by the yield stress of the material. And of course, Murakami and others applied this to additive manufacturing components starting from titanium alloys and 74 SS steel alloys. And they studied different effects. I also made some tests for Fatemi together for understanding if the approach was working or not for sharp notches. We studied different cases of notches. This is a work by Reza Molaei and Ali Fatemi published in Crackpad 2018, but there are also some more recent papers by the same authors that you can easily find in the literature, where they studied the effect of the crack propagating from a notch component in presence of different parameters due to additive, for example, different build direction, different heat treatments, different HIP and not HIP configurations. So you can find a lot in the literature. And they applied the same criteria of Fatemi-Sossi, also keeping a more complex, but keeping also into account the Poisson's ratio and the ratios between Poisson's ratio to be able to estimate the Fatemi-Sossi parameters to the multi-axial fatigue case. And so they were able to summarize all this data in a nice way. These are all data from additively manufacturing components, from a tubular unnotched component and a notch component with a circular hole in a single scatter band. Very nice scatter band and results. Of course, dealing with this multi-axial approach, you can also consider that also the strain energy density can be applied under multi-axial conditions. But of course, I want to say, to be honest, that the physics is better explained by the Fatemi-Sossi parameter, because the physics behind the fatigue is completely summarized in this criteria. The strain energy density approach is more an engineering approach that is used, can be used also for multi-axial loading, but inside the physics about the phenomena is a bit less than this, because we are simply considering, or we are considering, the energy inside the control volume under multi-axial conditions. But still is a useful tool in that case. But as a teacher today, I want to show the most used criteria that is present, and also for giving you a different lecture. Personally, I prefer the strain energy density, not because I had developed it, but because the strain energy density does not need to take into account which is the critical plane. And for finding a critical plane in a complex geometry, you need 3 days. So, I mean, from my point of view, the strain energy density has some advantages with respect to the critical plane approach and Fatemi-Sossi approach. But on the other side, we can less motivate the physics behind this approach, and this is for sure another truth. So I want to leave you with this open consideration, I would say. And after that, I want to show you some example, very quickly, some current example of additive manufacturing, also for mentioning my collaborators that are working a lot for me and with me. I want to mention Javad Razavi, that made a lot of work on additive materials for a lot of time. And we work on different kind of materials, titanium alloys mainly, but also other materials, studying the fatigue properties of these alloys. I don't want to go much in detail on this, because my lecture was more on the local approach, but I want to show you in some examples of what we did. And of course, we consider different technique, selective laser melting technique for 3D printing components, but also other techniques for having a comparison between different techniques and the fatigue life of different materials. We study all the microstructures of this material, especially of titanium alloys, and we consider different kind of geometries, smooth specimen, semicircular notch, V-notch specimen, and other geometries. We print the samples with different size. We made different heat treatments, and we studied the microstructure of SLM samples after the process. We study also the microstructure very well. We studied the properties of the SLM material and also of the traditional material, and we compare together. And after that, we plot different fatigue curves dealing with this material for a notch and notch components. And we apply, of course, our criteria, that is the strain energy density, taking into account also the defects and the volume of the material that we calculate for these titanium alloys, that gives us a radius R0 of 0.33 millimeter, and we were able to summarize everything in the same scatter band, again with the strain energy density, which is a local approach. After that, we made the same with the lens. So again, titanium alloys. I don't want again to go too much in the details. This is another well-known manufacturing process that can give you very nice components and very nice parts. And what we did is, again, to study different geometrical features, and again study the microstructure in details. Again, study what is happening, which were the main defects, the size of the main defects, the size of the microstructure interaction with the defects, all these considerations. And after that, a lot of experimental activities was done. That after that, we were able to summarize again with a good accuracy using the energy-based approach, both for a notch material and notch material, both for additively manufacturing material and also for traditional processes. After that, we also consider ABM under static and fatigue loadings. And here we study the interesting effect, which is the thickness or scale effect, that for me is always a key point that we have to consider in research, especially when we deal with fatigue issues. Due to the cost and limitation in printing, we consider up to now only limited number of cases, but this number of cases were able to show us how strong is this effect in the fatigue design, and how is this affecting the final fatigue behavior. Again, we study the microstructure that is changing according to the thickness due to the process itself. And this is, of course, affecting the fatigue life. This is actually the real surface that you can see along the notch edge due to the process. And so you can see that you have a lot of, it's not a nominal surface, you have a lot of difficulties to model it properly if you want to consider all the physics behind this phenomenon. But at a certain point, we need to have an engineering tool for design. So we need to have a compromise between what we want to understand as material scientists and what we want to predict as engineers. So we have always this competition. Is like a competition between fracture toughness and strength. You cannot increase the toughness and increase the strength in the same way. So here is the same. And again, we made a very nice synthesis dealing with the fatigue resistance of this material. And again, we applied the strain energy density. Here is the summary of the results. What it is very interesting to know is that we consider as built configuration. You can see how much it is reduced the fatigue life with respect to machined and with respect to conventional process, if you don't are able to really treat well the surface. Titanium alloys is high strength material, so as I said before, it's very sensitive to the defect, and you have to be very careful how to manage it and you treat it for fatigue purpose. And after that, I want to show you some funny topic that I'm developing right now that is mainly due to this guy, a professor that came from US and now is in my team in NTNU. Is Professor Chao Gao. We are working on additive manufacturing and specifically on interlocked behavior that is mimicking nature in additive components. And so what it is very interesting is that in different kind of natural structure, you can find these interlocking mechanisms that are able to increase the fracture toughness, but also the fatigue life of a component. And with the actual technique in additive manufacturing, we are able to print these materials properly, these interlocking structure properly, and we are able to estimate which is the advantages that we have in terms of fracture toughness and fatigue strength. So we did several studies on this, and we compare different kind of interlocking between material. This is actually the real geometry that we have. Here is an example, is the almost non-interlocked structure in comparison with the complete interlocked structure. You can see that actually you increase of 50% the almost the maximum strength that you obtain, and almost you increase of 3 or 4 times the fracture toughness considered as the integral of the area behind below this curve. So it's very nice to see how the component fails in this experimental test. This is an experimental test. You start to see the dot, the white points where the failure is happening, and so you see how this is failing. Very nice work. And this is another example. And after that, we are working more with this with the PhD student that is in collaboration with Caltech, with Julia Greer from Caltech in US. And we are studying interlocked structures using also data-driven approaches, which is almost machine learning or artificial intelligence, to predict very well how we can estimate the toughness, the ultimate strength, and the elastic and the stiffness of our components with different interlock configuration, being able to predict it with a data-driven approach that is nowadays, well, I think a hot topic of research. And what we are also doing is to make some tests. I want to mention here Anikao, that is another, the right pronunciation is Anitsao, that is our PhD here with me and Chao Gao. And we are working on fatigue of cellular structures. And we have studied different configuration of irregular cube, for example, where we have seen different way of failures. So we made the fatigue test, we monitor everything, and we understand how the component was failing with this geometrical configuration of the cellular structures. After that, we study irregular star configuration. This is a nice collaboration with the University of Trento, by the way. And we study also in this case the failure pattern. I don't want to show you all the video, that can become boring, but we made a lot of this investigation. We are also using DIC for seeing the displacements and which is the strain distribution inside the component. We studied the regular star, that is another case. We studied the trabecular case. We studied the irregular X. We studied the regular X, but a paper will now be online soon in fatigue and fracture dealing with this topic, so you can find it easily. But about this architected cellular material, I would also suggest to you to read this recent paper that we have published in Material Science Engineering R. So 6 years later, I published with Professor Lazzarin. I was able again with Professor Ricci and a collaboration with South Africa, Anton Duplessis, and a strong collaboration with Matteo Benedetti and Dal Lago from Trento, and my close collaboration with Javad Razavi, which is my closest collaborator here in NTNU, to publish this work that is 60 pages of review dealing with fatigue properties of cellular materials, just published this year in this prestigious journal that has a impact factor of, in the next 5 years, that is almost 43. And of course, as you have seen with Jan, we are also working on cellular structure from other perspective. What it is very important to see or to understand is that actually, cellular structures have also other functionalities, not only the structural integrity part. They can be used, for example, in different energy storage applications. And what Yang has proposed present to you, I think, is close to this, is linked to the ERC starting grant that he get this year in 2021. And we are working on this topic. Of course, my part on this project is the part related to the structural integrity, because I'm always working on that. But I mean, this is another interesting application of cellular structure that is, of course, in collaboration with Stanford and other prestigious institutions. If you see in the slides here, the metal electrode assembly is a very complex material. I mean, combination of materials that can really create a lot of problem in terms of structural integrity. And nowadays we have the possibility to play a lot with the geometrical effects that we can create on cubic lattice or carbon paper to create a better electrode for our component. This is not only affecting the structural integrity, it's affecting the electrical conductivity and the permeability of the component. But again, structural integrity plays a fundamental role, and especially fatigue is the cause of failure of many of these components under service conditions. So we need always to consider these aspects in our applications. This is another example where we are comparing different effects of lattice structures, and which is the permeability of this as a function of the porosity. A nice picture as initial study of that Yang has given to me for this specific presentation. And we are discussing the microstructure selection as a function of permeability, conductivity, mechanical integrity, temperature distribution, corrosion, design trade-off, and separation of multi-phase flow, because also the flow is so the flow dynamics problem is very important in this case. And after that, we are also working on additive manufacturing, dealing with designing fatigue structure inspired by nature that are less sensitive to fatigue design. Actually, ideally, we would like to design structures that are fatigueless, but of course you have always the limit of the material, but geometrically we can design something that is fatigueless if you are able to play very well with the geometry, as we can do with additive components. And so we are working on this, dealing with a tool that is again an additive manufacturing tool, and together with the data-driven approaches. And this is the PhD Shimbo Wang that is with me working on this topic. That is one of my main recent interest in research. This is the first estimation what we are able to predict with a very good accuracy using the SED in combination with data-driven approach with the convolutional neural network for different kind of notch geometries under fatigue loading. And of course, the topic is not, we are not only the one working on this topic. So, I mean, the topic is not so bad if also people from Caltech are working on this. This work, for example, is from Michael Ortiz, dated 2019, where he's applying a data-driven approach to this kind of notch components. Of course, a very simple geometry, but the message is very meaningful because is able to predict with different constitutive laws the final behavior of the component. And after that, together with the Caltech, we are still working on 3D architecture materials. And here is again a topic of Marco Maurizi that I have introduced to you before. He's working a lot on this topic of truss-like lattice and other combination at very small scales. So what we are trying to do is to study this component that is reported in the slide, the scale of the test. So if you see, the edge of this component is 100 micron, and we are studying the propagation of this using a three-dimensional model with XFEM to propagate properly the fracture, to estimate properly the fracture behavior, and to compare it with the experiments at the nanoscale, I would say. And here is the first estimation that we did. You can see the crack propagating. And in the plot, you can see the red curve that is the prediction compared with the experimental results. So actually a very good agreement between prediction or assessment and experimental results. Again, this is print with additive manufacturing. This is a polymers. This is a polymer. We are considering different material, but we have polymers or other material that are obtained at micro and nano scale. So with this, I want to conclude this presentation. I hope that you find this talk interest. I start from the very beginning of fatigue. I go through some local approaches that I consider interesting, always maintaining the connection with additive manufacturing problems. So discussing defect, multi-axial problems, and also discussing the problem of notches that, of course, are always present when we are designing against fatigue and when we have additive manufacturing components. And after that, I show you some recent trends of my research or recent topics that we are making here in Trondheim, dealing with some new topics that I like to share with you today, and that I hope you find of interest. So thank you so much for your attention. I spoke 4 minutes much, but I hope you can forgive me for this. Thank you.
Thank you, Filippo, for your comprehensive presentation of local approaches and for this very nice overview of your current research. If there are any questions.
Yes, I have some question. My name is Angel Cernescu, and thank you very much for this interesting presentation. First, it's about the ROSTAR radius that you have introduced in local approach.
Okay, so ROSTAR?
I want to talk about the local approach more.
Okay.
Yes, and in this the first approach that you mentioned which use the rho star radius. Is there any specific rule to find this rho star radius?
This is a good question. Actually, when originally Neuber and Radai start to use this approach, they actually study the problem considering this rho star like a material property that they were able to detect from some experimental tests. So at the beginning, it was more a kind of trial and error approach to identify which was the rho star working better for some materials. But after that, they were also able, Radai and after that me and with Lazari were also able to provide an equation for this rho star, and the equation is very similar to what you have for the critical length approach in the theory of critical distance. So it is again linked to the in static to the ultimate strength of the unnotched material, and and to the fracture toughness, and under fatigue is linked to the fatigue limit of the unnotched component and to the threshold value of the crack component. So again, you can find this rho star like this. Usually, to be honest, I didn't in my research because when I started in 2001, 2002 to look to this, there was just a plot also in the standard that is also reported in the FKM standard in German, where they put a graph reporting the value of rho star for different materials. So I didn't investigate much how to obtain these values. But I think the idea is that is the same of the theory of critical distance and also the same of the R0 that we use for strain energy density in some regard.
Oh yes, did you mention now about R0, the radius of control contour?
Yes.
I've seen something that I don't get the explanation for what the strain energy density from a tensile, uncracked tensile specimen should be equal with the strain energy density in a cracked specimen.
So the assumption of the method is that if the failure, the initial idea of the criterion is to apply it to brittle failure. So under linear elastic hypothesis. So the initial idea was to say if the energy is the governing parameter for the design, we need to verify that the energy is also is able to predict the failure of unnotched components and of the most critical notch components, which is the case of a sharp crack. So if these two energies are equal to each other, this means that the criterion is working well. And so we estimate the radius of the critical radius of the volume, imposing that the two energies are equal, and we have this kind of estimation of R0 that is a gain function of the fracture toughness and tensile strength, with the addition that we are also able to consider the Poisson's ratio because the strain energy density is implicitly three-dimensional approach. But of course, I agree with you that in some practical case, you have different energy for especially if you have ductile extended or a big ductile behavior. This is not true.
Yes, because my next question would be how valid are these local approach to tough ductile polymeric materials?
Yeah, what we have I have a double. Okay, so when we start this for polymeric materials, we made a lot of work with Professor Manuel Eliches in Spain, and actually we proved that the method was not working well at room temperature for unnotched material, but it was working well only when we were able to obtain for unnotched material a brittle failure. So we go down with the temperature until minus 30, minus 60 degrees. But for notch components, we also proved that any kind of notch components is very well predictable also at room temperature, because the stress strain curve that you have for a notch components, due to the effect of the notch hardening effect close to the notch, give you a more linear trend of the stress strain curve close to the notch tip, and this make the criterion apply again very well. So my answer is that you can apply it to polymers, but it's not smart to apply to unnotched polymers, because unnotched polymers is, and in that case also the question how to evaluate the critical radius arise, because if you cannot compare, so what we did in the past was to compare to evaluate the critical radius, to compare a blunt notch, strain energy density of a blunt notch with the strain energy density of a sharp notch. And so to evaluate the critical radius like this, because the unnotched specimens are simply impossible to predict. The plasticity is too huge and the mechanisms are completely different. But this is the drawback of every criterion that is assuming linear elastic hypothesis. The theory of critical distance has the same problem, the fictitious notch radius has the same problem, and the stress intensity factor or notch stress intensity factor has the same problem.
Okay, thank you very much.
Thank you.
Thank you. I also want to thank you. There are other questions because
a short question and a short comment, if it's possible.
Okay, please.
You talked a little bit about the threshold value and respectively A0. So question is, do you think the threshold value is a material property or not, respectively A0? Because you show the table there in which there were some materials and A0 had, let's say, a fixed value, right?
Yes.
So is it a material property or not?
As an engineer, I would say yes. But it's always the perspective in how you look to it. I mean, is an estimation of, I think is a material property, but is also depending on the environmental condition where you are. Because if, for example, you consider the same material at different temperature, A0 is changing. So it's sensitive to the environment. So A0 is a material properties, but is also function of something else. And this is always the case. So I agree with you that this is open points, is not something where I can put a full stop.
Okay, thank you. Another comment is I enjoyed a lot last part of your presentation. You started to do very interesting things. We started to work also on this type of mechanical metamaterials. So here I think it's a lot of work to do in the future. Well, thank you for your presentation. Thanks.
I hope that we can collaborate on this if you like.
I hope also, and we started also, well, for 2 PhD thesis with this convolutional neural networks and all kind of these types of topology optimization. So here it's, I think.
For us, it's a pleasure if you want to share with us, and we can share with you whatever we have.
Sure. Thank you very much for your presentation.
Thank you, Professor Constantinescu. Thank you, Filippo, again. So we will have break till 11:30, and then we will restart our online meeting. So thank you again, Filippo.
Thanks a lot to you.
Livio, sorry.
Yes.
Can I make an announcement?
Yes, please, Roberto.
Okay, sorry. I would like to remind to all the participants that if they want to take part to the final test, please write me an email, let's say before the end of the next lecture, in order to arrange the list of the participants to the test. So please, not later than 1 o'clock Central Europe time, send me an email asking for taking part to the test. Thank you.
Thank you. Also, I would like to announce that all the lectures since now are on Unicampus and can be downloaded. The only it's split in two, the lecture of Professor Auricchio is split in two. So today I hope to upload these 2 lectures from today. Okay, so have a good break.
1 second, if it's possible, Professor Marșavina.
Yes.
Regarding lecture 8, the PDF conversion is not too great.
Yeah, I know.
There are some parts missing from the presentation, so if the lecturers can re-upload, it will be great. Thank you.
Okay, I know. It's the lecture of Professor Auricchio, no?
Yes.
Yeah, I saw. Okay.
Okay. Thank you.